Alrighty, so this is the June 2015 Unit 1 paper, the last paper for the old specification. So let's get started. We're going to look at some atomic structure to kick off. So we've got 5 statements that refer to isotopes and some radium isotopes. So we've got, let's have a look here. We've got radium-223, 224, 225 and 226. The isotope with the smallest mass number is obviously the one with the smallest top number, so 223. The isotope with the most neutrons must be this one over here. They've all got the same number of protons, so a higher nucleon number must mean a higher number of nuclei. Isotope with a nucleus that has the largest specific charge is going to be this one, because it has the smallest mass, but they all have the same charge, so it's going to be that one. Okay, so then we've got an isotope decays by beta minus decay to form 22589. So beta minus, the nucleon number doesn't change, so it must originally have been 225 as well. And isotope that decays by alpha decay to form 220. Alpha decay removes 4 nucleons, so it must have started as 224. So that's going to be that one right there. Okay, so an atom of one of the radium isotopes in table 1 is ionized, so it has a charge of 3.2 times 10 to the minus 3, and that's plus 3.2. State what happens in the process. Well, what's happened is if it's got a plus charge, you must have removed electrons, and if it's got 3.2, that means 2 electrons have been removed. Okay, so then we've got the next question looking at, I guess we're going to need to move both. Alright, so the specific charge of the ion formed is 8.57 times 10 to the 5. Deduce which isotope in the table has been ionized. Assume that both the mass of a proton and the mass of a neutron is 1.66 times 10 to the minus 27. So we know its charge and we know its specific charge, so the general equation is if this form here, charge divided by mass. So if we want to get mass, we need to divide the charge by the specific charge. So that's 3.2 times 10 to the minus 19. 19, that's the charge. The specific charge, it said, is 8.57 times 10 to the 5. Right, so let's do that so we can work that out. So 3.2 times 10 to the minus 19 divided by 8.57 times 10 to the 5. And that gives us a value of 3.73 times 10 to the minus 25. Let's divide that by the mass of one nucleon, minus 27. And that gives us 225 as the isotope there, so it was 22588 Ra, or radium there. Okay, so that finishes off that first question there. Okay, so the equation shows an interaction between a proton and a negative kaon that results in the formulation of a particle X. State and explain whether X is a charged particle. So let's apply conservation of charge. So going through, we've got a charge of -1 for the K minus, we've got +1, so we've got an overall charge of 0 on the left hand side. We've got +1, 0. So essentially we know that the particle must be -1 in order to conserve charge. So let's state and explain that. Alright, so it must be negative charge, or have a charge of -1 in order to show that charge is conserved. Okay, so then state and explain whether X is a lepton, baryon, or a meson. So if we have a look at the equation, on the left we've got a baryon number of 1. Currently we have a baryon number of 0 on the right hand side, so it must be a baryon in order to conserve baryon number. So let's get that down. Alright, so that's what we've got there. It needs to be some sort of baryon. Okay, so let's continue on. State the quark structure of a K minus, K plus, and K0. Wow, they're really giving away marks with this one. So, to make a K minus, we're going to need a strange quark, giving us a charge of minus a third. So then we're going to need an anti-up quark to give us the overall minus charge. K plus is the exact opposite, because it's the antiparticle. There, so that's going to be an anti-strange. K0, it must contain a strange quark and a anti-down, or we could have gone with a down anti-strange. Those two end up with exactly the same, so it could be either of those two. Okay. So strangeness is conserved in the interaction. Determine, explaining your answer, the quark structure of X. Okay. So strangeness is conserved. Let's rewrite the equation so we can map it out. So we've got a K minus and a proton, and that produces K plus, K0, and something. Plus blank. Okay, so let's do this in terms of strangeness. A K minus, we can see, has a strangeness of -1 because it's got a strange quark. A proton has a strangeness of 0. K plus, we can see, has a strangeness of +1 because it's got an anti-strange. A K0 could be either +1 or -1, depending on which of the two it is. And then, so we've got -1 currently on the left, and then over here we could have got +2, or we could have 0 there. And we know it's not going to be +2 because there's no way we can turn that into -1. So that we can eliminate that as an option there. So it's currently 0. So we need a strange. We need a strange to -1 to do this. So it's going to contain a strange quark. But we know it's neutrally charged. No, hang on. What did we have before? It has a charge of -1. Strange. That's going to be an anti-up strange there to give us a charge of -1. In order for this to work, except that's not right because we know it's a baryon. So correction, let's get rid of that. So we know it contains a strange quark with a charge of -1/3. We need it to be a whole third, so we're going to stick in 2 downs in order to give that. Or actually, we could start with a strange of +2, and you can have a strange, which would actually reverse what I talked about before. So those are either of those options, depending on which particle it is. So I picked that it was the one with -1, which gives this one. If it was the one with +1 strangeness, it would lead to the 3 strange particle here, there. Okay, so that's that question complete. Okay, so baryons, mesons, and leptons are affected by particle interactions. Write an account of these interactions. You should include the names of the interactions, the groups of particles affected by each interaction, and identify the exchange particles involved in the interaction. You should give examples of 2 of the interactions that you mention. Okay, so we could go with, between baryons and leptons, we could go with weak. Between baryons and mesons, we could go with strong. And then between any charged particles, we could go with electromagnetic. So we have quite a few options to go there. So let's go along with that. So let's talk about the strong interaction first. Okay, so let's first talk about the strong force. So the strong interaction would occur between anything made of quarks, so any baryon and any meson. The strong force is mediated by exchange particles called gluons or pions. So that's the first one I have picked. Let's pick another one. Okay, so that's what we've got there. The baryons and leptons interact through the weak interaction because they are all fermions or will have non-integer spin. And the weak force is mediated by W+, W-, and Z bosons. So the one we haven't talked about yet is the electromagnetic interaction. Alright, so that's what we've got there. Electromagnetic goes between charged particles and it's mediated by virtual photons. So let's see how we're doing against the criteria given. We've got the names of them. Gravity is insignificant because it's so small. We've got the groups that they're affected by, yes. We've got exchange particles, and we've got examples of the two. So we just need to do some examples actually because we haven't actually got them. So what should we go with? So the examples I've gone with, protons and neutrons interact through strong and weak as they are both hadrons and both fermions. Protons and electrons interact through both weak and electromagnetic as they're both fermions and are both charged. So those would be your examples to use there. Okay, so that finishes off that one. So let's continue on. So flip on to the next question. So this question wants us to draw a Feynman diagram to represent a particle interaction. So let's go with a proton and an electron. Electron there. So they're going to exchange a virtual photon and go off still as a proton and as an electron. They're not going to be changed by the interaction. So we can see that the charge on the left has stayed the same, the charge on the right has stayed the same, so we don't need to carry a charge over, which is why we have a neutral exchange particle, the virtual photon. That's all we need, and the final thing, time is going that way. That's the passage of time showing protons and electrons interacting. Okay, so that completes that question. Alright, so we've got a sodium metal with work function of 2.28 electron volts, and an atom has an ionization energy of 5.15 electron volts. State what is meant by the work function. So the work function is the minimum energy required to remove an electron from the surface of a material. That's your work function. It's fairly straightforward. Okay, so state what is meant by the ionization energy. So let's get that one in. Okay, so we've got ionization energy is the energy required to completely remove an electron that is currently in ground state or from ground state. Those are your basic definitions that you just need to learn. Show that the minimum frequency of electromagnetic radiation needed for a photon to ionize an atom of sodium is about 1.2 times 10 to the 5. So we have the ionization energy 5.15. So let's first convert that into joules. And we do that by multiplying by 1.6 times 10 to the minus 19 times 5.15 gives us 8.24 times 10 to the minus 19 joules. That's the energy. E equals HF for a photon energy. So the frequency is going to be that energy. So 824 times 10 to the minus 19 divided by Planck's constant, which you should have basically memorized by now, 10 to the minus 34. And if we do that calculation, 6.63 times 10 to the minus 34, bracket, we end up with 1.24 yada 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 times 10 to the 15 hertz, which is roughly 1.2 times 10 to the 15, so 2 significant figures there. And that finishes that one. Okay, so we've done that, so let's move on to the next question. Electromagnetic radiation with the frequency calculated in part B is incident on the surface of a piece of sodium. Calculate the maximum possible kinetic energy of an electron that is emitted from the surface to an appropriate number of significant figures. Okay, so the max kinetic energy is calculated by doing the photon energy minus the work function. So that was 8.24 times 10 to the minus 19. That was the photon energy. And we had the work function. We need to calculate, what was it, 2.28. We need to multiply that, turn that into joules, minus 19. So let's do that calculation now. And we end up with a value of 4.592, so that's going to be 4.59 times 10 to the minus 19 joules, and that's going to be given to 3 significant figures because the data given in the question is 3 significant figures. Okay, and it wants the speed, calculate the speed of an electron that's the same de Broglie wavelength as the electromagnetic radiation in part B. So we first need to work out what the wavelength is. We're going to use the wave equation for that. Like this. So the wavelength was c over f. So that's 3.00 times 10 to the 8. And the frequency was 1.24 yada 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 times 10 to the 15. So let's calculate that. 3 times 10 to the 8 by 1.24 times 10 to the power of 15. And that gives us a wavelength of 2.41. I'm not going to round this. I'll keep it in my calculator, but it's just so you know what I've got. So that's your wavelength. Using your de Broglie equation, wavelength is h over mv. So v is h over m lambda. So that's going to be 6.63 times 10 to the power of minus 34 divided by, it's an electron, so 9.11 times 10 to the minus 31 times answer. And that gives us a value of 3008. So let's give that to an appropriate number. Let's go 3.0 times 10 to the 3 meters per second as your final answer there when you put those values in. Okay, so that should finish off this question 4. Let's carry on. So moving on to some DC circuitry. Sketch on figure 1 the current voltage characteristic, which should really be current potential difference characteristic for a filament lamp for current up to its working power. So again, something you should just know what it looks like. That went a bit crazy. Sorry, that's so wobbly. But essentially what the features you should have is a roughly straight line section going through the origin. I haven't shown that very well in the middle. And then the gradient decreasing towards the ends as the resistance increases. So that's your graph. State what happens to the resistance of the filament lamp as current increases. So this is just state, so what happens? So what happens is your gradient decreasing, that shows the resistance is increasing. Okay. So state and explain whether a filament lamp is an ohmic or non-ohmic conductor up to its working power. So an ohmic conductor should current and potential difference should be directly proportional. The graph does pass through the origin, but it's not a straight line, therefore it's not an ohmic conductor. So that should finish us off for that one. Okay, so let's flip over. So we've got 3 identical filament lamps, P, Q, and R. I'm guessing one of these is about to fail. Let's have a look. So the filament in Q melts so that it no longer conducts. Explain why P becomes brighter and R becomes dimmer. Okay, so Q is melted. So if we have a look at our diagram, this one's Q. So what's going to happen is now all the current has to go that way around the circuit. So let's first explain why P becomes brighter. So that one is the easy one to get. So all the current now has to go through P. So power is directly proportional to current squared. So if current increases, power and brightness now increase as well. Let's fix my grammar. Okay, so that's the easy one. The harder one to realize is why R becomes dimmer. So let's do that one too. Okay, so the first thing to recognize is when you take out parallel components or you shut off those pathways, total circuit current will increase, and you can try that out with some resistor laws if you like. So the effect of that is that the current in your circuit is going to decrease as if you've kept the EMF the same and the resistance has increased. Current through R therefore decreases because the whole circuit current goes through R, and therefore power is going to decrease, and so is brightness because power is directly proportional to the current squared. So that's that question there. All right, let's continue. Ooh, this is a long question, 5. Anyway, so a filament lamp X is rated at 60 watts, 230 volts. Another type described as energy saving has the same light intensity output, but is rated at 11 watts, 230 volts. So smaller power, you can see it's has smaller energy input, so it's going to be energy saving. Calculate the electrical energy converted by each lamp if both are on 4 hours a day for a period of 30 days. Okay, so the equation we are going to be using is E equals PT. So the energy of X is going to be 60. They're on for 30 days, 4 hours a day. To convert that into seconds gives us an energy used of 2.59 times 10 to the 7 joules. Energy used by Y, again, still going to be PT, but instead it's 11 times 30 times 4 times 60 times 60. And if we do that, we get 4.75 times 10 to the 6 joules. So you can see there's considerable energy saving going on there. Alrighty. Suggests why the 2 lamps can have different power ratings but have the same light intensity output. So this is all to do with the energy wasted by a bulb. So first thing, lamps waste electrical energy in the form of thermal energy. So although they produce light, the older bulbs anyway certainly produce a lot of heat too. So lamp X is clearly wasting much more energy as thermal energy, perhaps because it's one of the old type filament lamps rather than one of the new fluorescent type lamps. Okay, so that completes question 5. Let's continue. The potato cell question. Those of you who enjoy these things, there's a great Hitler Reacts video about this question on YouTube, posted after the exam in which this was in. I had no idea why. This is very straightforward because it's just a cell. It tells you that, but never mind. If you want a distraction, do check that video out. So a potato cell is formed by inserting a copper plate and a zinc plate into a potato, essentially making it a battery. The circuit shown is used in an investigation to determine EMF and internal resistance of the potato cell. So this looks very similar to an internal resistance and EMF experiment you should have done as part of the course with a variable resistor. Let's zoom out a little bit so you can see. Okay, so first off, state what is meant by electromotive force. All right, so that's what we've got there. I don't know why we've got so much space. It's the work done per unit charge by a power source and represents the maximum energy that your charges will have at any point in your circuit. So that's that one. Okay, so we've got a graph of the what should be potential difference against current, or terminal voltage against current for this experiment. So it looks like this, pretty much as you should expect having done this experiment. All right, so that's what the graph looks like. So suggest what has been done to obtain the data from the points. So what's been done is the variable resistance has been changed, which alters the potential difference in current, giving you the values there. Okay, so that's that one there. So it says the EMF of the potato cell is 0.89 volts. Explain why the voltages plotted in figure 4 are always less than this, and why the difference between the EMF and the plotted voltage becomes larger with increasing current. So first of all, the terminal voltage, or the voltage across the rest of the circuit, is going to be the EMF minus the current times the internal resistance. So in terms of why this is always less, the current is never zero, therefore those two are, there's always a value subtracted from the EMF, so terminal voltage is always less. So let's put that down first. Okay, so that's what we've got there, and why the difference becomes larger. Okay, so let's address that. So we've got larger currents, there's a larger potential lost across the internal resistor, so that acts to decrease the terminal voltage. Okay, so that's that one there. Alrighty, so using the graph to determine the internal resistance, we're going to essentially need to determine the gradient. So I can't show you doing this because I can't flip backwards and forwards between the slides, unfortunately. But if you draw a straight line of best fit, the gradient of the graph should be, if you use a very large triangle, which you always should, so as much of the graph as possible, you should get a value, or that essentially I got the value of 2,650 when I did this, which means the internal resistance is going to be 2.7 kiloohms. So that's pretty large, but it is a potato, not a regular battery, so that's not entirely surprising there. Okay, so the next one I'm guessing is going to give us the EMF. Okay, so a student decides to use 2 potato cells in series as a power supply for a light emitting diode. In order for the LED to work as required, it needs a voltage of at least 1.6 volts and a current of 20 milliamps. Explain whether the LED will work as required. So first off, if we go to our graph and go to 20 milliamps, we can see what EMF we will get, what terminal voltage we'll get from each of our bulbs, and we can add them together. Okay, so if you read off 20 milliamps from the graph, you get about 0.33 volts, giving a total of EMF of 0.66 volts when they're in series, which is not enough. Or you can do it another way, you can read off 0.8 on your graph, which again, they don't lead to a high enough current. So again, that's not going to work. So you can argue it either way. This is the way I've gone about it. Okay, so let's move on to the final question. Okay, so I can sense a longer answer question coming, as we haven't had one yet. So we've got a cable used in high voltage power transmission is 6 aluminium wires surrounding a steel wire, and the cross section we can see. Resistance of a length of 1 kilometer of steel wire is 3.3 ohms. The resistance of a length of 1 kilometer of aluminium wire is 1.1. Steel wire has a diameter of 7.4 millimeters. Calculate the resistivity of steel. So we're going to want our resistivity equation. Resistivity is resistance times A over L, which is resistance times pi, or we got D squared over 4L. So let's put those values in. So resistance of steel is 3.3 times by pi times by 7.4 times 10 to the minus 3 squared divided by 4 divided by 1000 because it's a kilometre, giving us a value of 1.4 times 10 to the minus 7 ohm meters as the unit of resistivity. That seems very generous of 4 marks, but hey, you've got to take them as they give them to you. So explain why only a small percentage of the total current in the cable passes through the steel wire. So essentially, we can, if we have a look, the resistance is much higher. It's going to have the same potential difference, so it's going to be a smaller current essentially there. So let's put that into words. Okay, so the first thing I should have said, let's fix that a little bit. Let's go with resistivity. The resistivity of the steel is much higher, so for the same potential difference, it's going to have a smaller current. So we've got a lower current through the steel because of the resistivity. We also have 6 aluminium wires in parallel, so there's a larger aluminium cross-sectional area, giving a lower aluminium resistance and so a higher current. So both of those things will lead to a smaller, sorry, if I should be specific, higher in the aluminium there. So both of those things lead to a smaller current in your steel. Okay, so that's that one right there. So let's continue on. Potential difference across a length of 1 kilometre is 75 volts. Calculate the total power loss for 1 kilometre length of the cable. So the first thing we're going to need to do is work out the resistance of it all. So we've got 6 aluminium cables in parallel, each with a resistance of 1.1 ohms, and we've got one of just 3 ohms because that's the steel. So 6 divided by 1.1 plus 1 divided by 3, 1 divided by the answer, 0.172 ohms. There is the total resistance of it. So we can now use P equals V squared over R because we've got the potential difference and the resistance. So 75 squared over 0.172 squared divided by answer. Whoa! This is a really rubbish power cable. 33 kilowatts. Two significant figures there in your wire, which is pretty colossal, I think you can agree, and a pretty rubbish power cable. You're going to want a lower potential difference than that, realistically. Okay, so that completes the questions on this exam paper. I hope you found that useful, and I hope you found my update where I'm not using my handwriting for the written questions useful, so you can actually read them. Thank you very much for taking the time to watch this. Do look out for further videos. I'm now going to move on to the Unit 2 videos. I've already made videos for Unit 4, 5 and 1 is now complete, so do make use of those, and thank you for spending the time on Burrows Physics.